There are three rates of change that come up frequently in business situations. They are the rates of change of revenue, cost, and profit with respect to the quantity of items produced and sold. When dealing with the rate of change with respect to quantity, we can think of it as the amount that revenue, cost, or profit will change by if we produce and sell one more item. The rate of change of revenue with respect to quantity is called marginal revenue. The rate of change of cost with respect to quantity is called marginal cost, and the rate of change of profit with respect to quantity is called marginal profit. Like with any rates of change, these three rates of change can be found using derivatives. So in example 1, we have the cost of producing x units of a product, and we have the function that gives it. C of x equals x squared minus 3x plus 3,000. So we want to find the marginal cost of producing the xth unit. Well, the marginal cost is just c prime, the derivative of cost. That gives me 2x minus 3. So this is the marginal cost. When dealing with marginal cost, revenue, and profit questions, there are a number of formulas which will be useful in solving problems. The first is the fundamental relationship between cost, revenue, and profit. The profit is always the revenue minus the cost. The second formula to keep in mind deals with situations where a demand function is given, which relates to the price point necessary to sell a given quantity of product. To sell more product, the price must be lowered, and if price is raised, the quantity sold will diminish. This demand function is often denoted as P of x and gives price as a function of quantity. Basically, the x is the quantity, the P is the price. Demand functions can be used to calculate the revenue as a function of the number of items sold. The revenue will always be the price multiplied by the quantity sold. Basically, we sell x things at price P, the revenue is going to be the price times the quantity. P times x. So example 2 here, we have a demand function given. The demand function is P of x equals 200 e to the negative 0.2x. Here we want to find the revenue as a function of quantity sold and find the marginal revenue function. Well, the revenue is always P times x, which is going to be 200 e to the negative 0.2x times x, which basically gives you 200x e to the negative 0.2x. Now if we want to find the marginal revenue, we've got to take the derivative of revenue. Okay, so when we do this, we're going to use the product rule, so we're going to take the derivative of 200x times e to the negative 0.2x plus the derivative of e to the negative 0.2x times 200x. The derivative of 200x is 200. The derivative of e to the negative 0.2x, well, we're going to use the chain rule. We've got e to the negative 0.2x, and we have to multiply by negative 0.2. So we're going to have negative 0.2 e to the negative 0.2x all times 200x. And again, we could simplify it, but this is fine for the marginal revenue.
Here we're going to explore some of the applications of derivatives to business and economics, and it's really going to be a lot like the optimization problems that we've done, just putting it into a business context. In the following problem, we're trying to maximize profit, and what we're given is a revenue and a cost function. So we have that the daily cost is given by this C of x equals x cubed minus 6x squared plus 13x plus 15, and that the revenue that this firm generates is R of x equals 28x, where x is the number of products or items that they're selling. And so it's asking us to maximize the profit. And again, this is going to be exactly like the optimization problems we've done in the past. We just need to figure out a formula in one variable for profit. And so what we'll use is the fact that the profit is going to be equal to our revenue, so the amount of money we generate, minus however much it costs us to produce those items. And so we get our profit function right here, the sort of simplified version of it, minus x cubed plus 6x squared plus 15x minus 15. And really what I want to do now is optimize this. So again, taking the derivative, set it equal to 0. So here is the graph of the profit function. So it looks like somewhere within here we'll maximize the profit that we're creating at this firm. So in order to maximize that profit, we get the profit function, we find its derivative. So p prime of x equals negative 3x squared plus 12x plus 15. Set that equal to 0. It gets factored, and we can see that this has critical values at x being -1 and 5. And -1 doesn't make sense because you can't produce -1 elements, so it wouldn't be in the domain of our profit function. However, x being 5 is the point at which we will maximize the profit at this firm. And we saw that graphically, and now we've shown specifically that that is the highest point on our graph. This problem is slightly different in that we're looking at demand and revenue instead of cost and profit. So in this example, a swimming club is offering memberships at a rate of $200, provided that 100 people join. And then for each member in excess of 100, the membership fee will be reduced by $1 per person. And they're capping it at 160 memberships will be sold. And how many memberships should the club try to sell in order to maximize the revenue? So what we need to figure out is a equation for the revenue. So in order to do this, we first need to get a demand equation. And so our demand equation, we're going to call P equaling f of x. And we know that they're guaranteed at least 100 members and capped at 160. And we're assuming this linear relationship between all of them because for each person, for each extra membership that's sold, as x increases 1 unit, y will decrease 1 unit. So for every membership that's sold, they'll decrease the price by $1. Because we have this linear relationship, we know that we can figure out what the slope of that line is going to be and come up with a demand equation. So you know that for sure they're selling 100, has to be 100, and at that point it's $200 per membership. And it's capped at 160, so you know that 160, and then at that price it would be $140 for the membership. And we know that that will be then the slope of the line. So we can come up with an equation for our demand, basically saying -x plus 300 will be a equation for the demand function. So once we have our demand function, we can figure out what the revenue function is by knowing that the revenue equals x, or the number of units that we're selling, times p, which is our demand function. So here we have our r of x. Our revenue is going to equal x times our demand function, which is -x plus 300. And again, if we want to optimize this, we take its derivative, we set it equal to 0, and then we solve and we see, okay, if they offer 150 memberships, that's the point where they're going to maximize their profit. Here we can see a graphical representation of our revenue function, and x equaling 150 is the point where we're maximizing our revenue, noting though that this function is really only defined for x being 100 through x being 160, because that's the cap that we're looking at this window for.
Let's talk about applications of the indefinite integral in business and economics. Something that is important to note in this section is that the total revenue is $0 if no items are produced. However, the total cost may not be $0 if nothing is produced. Take, for example, let's say you own a factory that produces tennis rackets. If you don't produce any tennis rackets, you're going to still have certain fixed costs like paying rent for the building or the warehouse or whatever, or maybe utilities like electricity and things like that. So that's something to keep in mind in these problems. Let's talk about example 1 that goes over total cost. Suppose the marginal cost function for a month for Mr. Kwan's boba is MC bar is equal to 2x plus 30, where x is the number of units of boba and cost is in dollars. If the fixed costs related to the product amount to $8,000 per month, find the total cost function for the month. So we have the marginal cost function is equal to 2x plus 30, and we want to take the integral of both sides. And if we integrate the left side, we're going to get the cost function, and then the right side, we would get, So we can rewrite it into two different integrals. And if we do that, we get 2x squared over 2 plus 30x plus, I'm going to write k instead of c since we have our cost function and we don't want to cause any confusion. So our cost function is equal to x squared plus 30x plus our constant of integration k. Now, we still need to figure out what k is, and we know that the fixed costs are $8,000, which means that that's another way of saying that c of 0 is equal to 8,000. So that's helpful because if we plug in 0 for x, the output is 8,000, and these terms will disappear, so we just end up getting k is equal to 8,000. That means that our total cost function is equal to x squared plus 30x plus 8,000. Example 2 says, suppose monthly records show that the rate of change of the cost or the marginal cost for a product is MC bar equals 3 times the square root of 2x plus 25, where x is the number of units and cost is in dollars. If the fixed costs for the month are $11,125, what would be the total cost of producing 300 items per month? So we have the marginal cost function is equal to 3 times the square root of 2x plus 25, and we want to integrate to get the cost function. So I'm going to pull out the 3. Let's write it with the 1/2 exponent. We're going to need to use u substitution, so I'm going to set u equal to 2x plus 25, and then du will equal to dx, and then I'm going to divide both sides by 2, and we get du over 2 is equal to dx. So we can make this substitution there, and then also replace u here. So c of x will equal 3 times the integral of u to the 1/2 power times du over 2. And I'm just going to pull out the 1/2. So we have 3/2 times the integral of u to the 1/2 power du. Now we can just use the power rule. So that's going to equal 3/2 times. We want to increase the power by 1. So 1/2 plus 1 is 3/2. And then we want to divide that by 3/2 as well, plus c. So we'll have 3/2 times, I'm going to multiply it by the reciprocal in the denominator so we can get rid of the fraction portion. And then u we determined was let's see, what was u? 2x plus 25, and that's going to be to the 3/2 power plus c. These will cancel each other out. So, I'm going to write this as k again. So c of x is equal to 2x plus 25 to the 3/2 power plus k. Now we need to figure out what our constant of integration is, and the beginning of the problem said that the fixed costs were $11,125. So that means that c of 0 is equal to 11,125. So if we plug in 0 into our function, the output will be 11,125, and that's going to simplify to 25 to the 3/2 power plus k is equal to 11,125, and 25 to the 3/2 power is 125. And then if you solve that for k, you get k equals 11,000. So our final cost function is 2x plus 25 to the 3/2 power plus 11,000. But the original question asks what would be the total cost of producing 300 items per month. So then we still need to evaluate C of 300, and that's going to be 2 times 300 is 600 plus 25 to the 3 halves power plus 11,000. And then if you simplify that, that ends up being 26,625. And the units on this is dollars since we're evaluating our cost function. So you could just write a sentence saying the costs of producing 300 units is $26,625, and that is our final answer.
A couple of econ formulas involving integration. Definition: if a company's profits rely on a function of time, like a pump at an oil field decreases its productivity over time, we say the company has a continuous stream of income. So if a company has a constant stream of income, like a subscription service or something, that would still be a continuous stream of income, but we wouldn't really need calculus to figure out like the total income over a period of time. So we're interested in streams of income that change over time. So the rate at which the money's coming in is somehow changing. It's probably decreasing, right? Like any kind of equipment depreciates, or like an oil field gets tapped of resources. So we're given a rate. We want to figure out like the total net amount of income we're earning from that stream of income. So given a rate, want an amount of stuff, that should trigger us. It's like, oh, we have to integrate. So if we have an expression for the annual or monthly or whatever rate of income given by our income stream, f of t, the total income from 0 to k years is given by just that. It's just the integral from 0 to k of that rate, right? Because the integral is the reverse of a derivative. And if we're given a rate, we integrate it to figure out the amount of stuff that happened. Example, find the total income over 10 years for a continuous income stream with an annual rate of flow at time t given by 8,500 e to the negative 0.2 t dollars per year. So you're going to see that a lot where it's like an exponential with it to the negative something t, because that gives you like a decreasing exponential curve. So it might start decreasing kind of a lot at first and then sort of level off, but it's still a decreasing function. If this were an increasing function, well, we'd be in good business because we just keep getting more and more income, but usually that's not the case. So that's a pretty simple setup. It's just the integral from 0 to 10 of 8,500 e to the negative 0.2 t dt. This would be one of those times where it's maybe good to pause the video and just try to do this on your own, right? You can do this. I just want to show you some good definite integral habits here to where you can do this with minimal fuss, and at some point it's just going to involve a calculator. So zap that constant outside. Right? We always want to take constants out because it just makes the final calculation a lot simpler. That is basically, that's a substitution now. We're going to say, okay, u is negative 0.2 t. But you see this kind of expression so much that at some point you should almost be able to do this without being able to do the substitution. What's essentially going to happen here? We're going to have to divide by negative 0.2. Because think about like the chain rule, if you were to take the derivative of e to the negative 0.2 t, would be multiplying by it. So to integrate that, it's just going to be e to the negative 0.2 t divided by it. But let's actually do it. So if we let u equal our little function of t up there, then du is just negative 0.2 dt, right? It's just the derivative of negative 0.2 t. Divide by that negative 0.2. So it's negative 1 over 0.2 du equals dt. In this case, well, 0.2 is 1/5, so it's like negative 1 over 1/5, so why not just call that negative 5? Punch it into your calculator if you don't believe me. So we're just going to have a factor of -5 that pops up in our final result. That's all. And that's going to come out front of the integral as well. What I kind of like to do with these is just ignore the definite integral for a second and just set up like the antiderivative, and then at the very end just punch in that 0 and that 10. We're not quite dealing with it yet. So the -5 comes out front. That gives you -42,500. And then just plug back in what u was in the first place. And now we're going to evaluate it at the upper and lower bound. So it's just that times e to the -0.2t. There's a way to do it in a definite integral where you change the upper and lower bound. I don't think we need to do that ever in this class, but if you were to take any kind of Calc 2, you would need to do that, but we can get away without doing it. All right, so just keep that constant on the outside and then just evaluate e to the -0.2t from 10 to 0, which means you just plug those in. So it's -42,500 times e to the -0.2 times 10 minus e to the -0.2 times 0. That second term is just e to the 0, which is just 1. You might be getting a little nervous here, being like, wait, isn't this number going to be negative? No, it's not. Trust the process. That thing inside the parentheses is also going to turn out to be negative. So the final answer, which is like net money, we would hope that that would be positive. Okay, so the first one just turns into e to the -2, right? Minus e to the 0, and then I would just use your calculator for all that, and just, again, trust the process. That comes out positive, and it comes out to $36,000, $36,748.25. Now suppose that we are taking our continuous income flow. As that money comes in, we are investing it. So we are investing it at continuously compounded interest, which is that formula A equals P times E to the RT. So that's technically the best way to invest money. Earning interest rate R, whatever it is. The present value of that income stream is the value right now of the income stream that we know will be earning money for the next K years. So let's say we want to sell our piece of equipment because it's getting old or whatever, but we know that that piece of equipment is going to be generating, not only generating interest, but not generating income, but generating interest on top of that income for the next K years. Taking that into account, like, what is this piece of equipment worth to us right now? And then later on, which is easier, we'll figure out how to do the future value, which is like, hey, what if we hung on to it for K years and then sold it? What's the value to us then? So companies make these kind of determinations when they decide whether or not to upgrade equipment or, you know, get a new factory or whatever. So if we have an expression for our income flow, f of t, then that's how you figure out the present value. So this is almost like working backwards in time. So taking that e to the RT that's going to be generating us income, if we multiply our integrand by e to the -RT and then integrate that, that's what gives us our present value. So that's the formula. You don't have to memorize it, just there it is. So there is a t inside the integrand. So we may write in that inside that exponent, so we may have to do some kind of a substitution or something on it. So here's an example. Okay, we have another continuous income stream. It has an annual rate of flow given by f of t equals 9,000 times e to the 0.12 t dollars per year. So that's still an exponential with a little small number next to the t. We want to find the present value of this income stream for the next 10 years if we're investing money at 6% interest. So let's think about our integral before we set it up. It's going to be the integral from 0 to 10 of f of t, which is 9,000 times e to the 0.12 t, and then times e to the -RT. So it's going to be e to the, now remember, it's not going to be 6, and I'm not going to tell you that. You never do math with a percent. It's going to be e to the -0.06 t. There it is. So we'll do a little bit of algebra first. First pull the 9,000 out. right? That's a good habit. And then just remember how exponent rules work. E to the 0.12t times e to the negative 0.06t, you add those exponents. So really it's 12t minus 0.06. I'm sorry, 0.12 minus 0.06 is positive 0.06. Okay, so it's an integral a lot like the last one. And just like the last one, now I'm just going to kind of skip this part because all that's going to happen is we're going to end up dividing by that factor of 0.06, right? So there you go. Let's jump right to that. So when you divide by that 0.06, it can of course come outside. So 9,000 over 0.06 times e to the 0.06t evaluated from 5 to 0. You divide by a number like 0.06, you get a bigger number, so that's 150,000. Again, just plugging and chugging. E to the 0.06 times 5 minus e to the what turns out to be 0, and e to the 0 is just 1. So that gives you, right, e to the 0.3 minus e to the 0, which, again, just trust your calculator. Double check. I would do the rest of this all in your calculator. That's what that gizmo is worth to us today, $52,478.82. So really, that's what we should sell it for, ideally. Okay, so that's present value. When we talk about future value, this is where we talk about, okay, I'm using K because it's K years. This is, now we're investing our continuous income stream. So it's like we're continuously investing it as well. That's why we need an integral. We're not just like taking a big chunk of it every once in a while and putting it in, you know, in an investment fund. So, right, P is the initial amount invested, or the present value. So that's the value of it, the future value after K years, depending on the rate R. So the future value is found like this. You just take that present value and you multiply it by whatever e to the RK is. Right, notice it's the same integral as last time. So we can essentially use the present value to easily determine the future value by just multiplying it by that factor of e to the r times however many years it is. Okay, so that's the future value formula. Example. A vending machine company is considering selling some of its machines. The income from these machines is a continuous stream with an annual rate of flow at time t given by f of t equals 12 times e to the negative 0.4 t plus 3. So this is an income stream that's a little bit offset by the factor of t plus 3. And then again, there's a negative in the exponential, which means this is a decreasing function, which should make sense because machines break down over time, right? It's not going to get more valuable in thousands of dollars per year. That shouldn't really matter, except at the very end, remember to put in, okay, it's that many thousand. Like if you get, 60 for an answer, well, no, it's 60,000. But for now, we just proceed. So we want to find the present value right now, and then the future value over the next 5 years if we're making 10% interest, which is pretty good. So buckle up, this one gets a little nasty. Present value is the integral from 0 to 5 of our income stream, 12e to the negative 0.4 t plus 3, times e to the, right, it's not 10 in there, it's 0.1, so it's negative 0.1 t. Really, this is going to be kind of the same as the last one, just the numbers are a little uglier. Take that 12 to the outside and then just combine those exponents by the rules of exponents. So I just went ahead and distributed those parentheses. So it's negative 0.4t minus 0.4 times 3, which is 1.2, minus 0.1t. That gives you what? E to the negative 0.5t minus 0.12. So again, just think about the substitution rule. We don't really have to do it. Just think, what's the derivative of that inner function? The derivative of negative 0.5t minus 1.2. The 1.2 doesn't appear in the derivative. So the derivative, du, is just going to be negative 0.5 like it was the last time. So all that's going to end up happening if you do the whole process is we're just going to end up dividing by negative 0.5. So you just do it. So it's 12 times 1 over negative 1 over 0.5, or just negative 12 over 0.5, times that expression, e to the blah, 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 evaluated from 5 to 0, because it's 5 years. And then we just kind of clean it up and plug stuff into our calculator as we go. Okay, so 12 divided by negative a half is the same as 12 times negative 2. And then again, okay, so it's e to the negative 0.5 times 5 minus 1.2 minus e to the 0 minus 0.12. So calculator time, apparently that's a negative 3.7, and that's negative 1.2. And then just stick all this into your calculator, however you do it, but in one big move. And you get 6.635. Remember, that's in thousands, so you could say 6.635 thousand, or it's probably simpler just to say $6,635.30. So like I was saying, the future value is just a number times that integral. So there's absolutely no reason to do the integral over again. We already did the work. We got the number. So just multiply that number by e to the r times however many years it is. Like that. So the future value is just like you take the amount that you're going to get from the investment, which is e to the 0.1, that's the rate, times 5, that's the time, times that number we got in the last one. So that's easy. If you have to do both in a problem, just do the past value first and then multiply by this number, or present value, I mean. Okay, and that's what you get, 10,939.75. So it's a lot more because you've been investing the money the whole time. But again, you're just taking into consideration things like, well, should I sell this machine now and get a new one? Stuff like that.
Welcome to P. Clark Calc, Practical Calculus for the Busy Math Student. And in this video, we're going to take a look at a specific business application of area between curves known as consumer and producer surplus. So here we're looking at an application of area between curves specific to business calculus. It's called consumer and producer surplus. And what it does is it measures the overall benefit to either the consumer or the producer thanks to the free market price of the item, so that people are paying a lower price than they would be willing to pay, or for producer side of it, they would be earning more than they would be willing to take for the item. So it starts off by looking at supply and demand, and if you graph them on the same axes, we end up with an intersection point, which in the world of econ is a huge thing. It's called the market equilibrium, and this determines the price of items. I mean, no one dictates the price of things in a free market economy. So in this example that we have here, we have a demand function modeled as the quadratic d of x equals 200 minus 0.5x squared. That's our blue graph. And then we have the supply function. Supply is an increasing function because as price increases, then the amount supplied would increase as well as more producers try to get in the market or producers increase what they are making. And so s of x here is 10x plus 50. And so what we did was we figured out where those intersected. Now, if you need to, you can do that algebraically by setting the two functions equal to each other and solving. It's a quadratic. I'll spare you the details on the quadratic there. But the solution, the positive solution to that quadratic is 10, and then you plug that in and we get our market price, or equilibrium price, of 150. And in our definitions here, we call this equilibrium point x sub 0, p sub 0. So if everything stays the same, this is going to determine how much of our product, 10 units sold per unit of time and at a market price of $150. So if we have the two functions, they have to intersect because by human nature, demand is a decreasing function, supply is increasing. And then what we do is we graph a third function, and it is the horizontal line at the market price, which is p sub 0. So we've graphed this third function, p0 equals 150. And what that does is it divides the region up into two parts. We have the upper region, which is the consumer surplus. It's between the demand function and the equilibrium price. And that's what determines, if you can draw this and you understand area between curves, that's what determines the consumer surplus definition, which you don't even really need to memorize if you know what you're looking at. But the definition is the integral of the demand function minus the market price with respect to x from 0 to x sub 0, which is the lower to the upper bound of our region. The producer surplus is the lower of the two, so it's the area between the market price and the supply function, which is the red region here. And so by definition, that producer surplus is the integral of the market price minus the supply function with respect to x from 0 to x0, the market demand. We'll begin by calculating the consumer surplus, so that's going to be the integral. The bounds of it are going to be from 0 to 10. The upper curve is the demand function, 200 minus 0.5x to the second minus the market price of 150 with respect to x. So this is the integral that defines the consumer surplus. And if we clean it up first before we integrate, we end up with the function 50 minus 0.5 x to the second. And that integral can be done by power rule. So our antiderivative function is 50x. Actually, easier to go fractions here. This is 1/2 x squared. So antiderivative would be minus 1/6 x to the third from 0 to 10. And then we can evaluate that. On the upper bound 10, we have 500 minus 1,000 divided by 6. And on our lower bound, that's going to give us a value of 0. So if we combine those, we end up with 3,000 over 6 minus 1,000 over 6. So 2,000 divided by 6 is our consumer surplus, which if we're working in American dollars here in our market, then we have a consumer surplus of $333.33. So as far as the calculus definition, producer surplus, it's just this region, this area between curves. And if we understand upper minus lower over the bounds of the integral, then we just go ahead, we can build that integral and evaluate whether we remember the formula or not. What it means in economics is this, that if we would pick one person, let's say we have x equals 1, say there's only one item available, the demand function at 1 is 199.50. So this person here, this guy here, you need these people, the people with more money than brains possibly to prototype everything. So he'd be willing to pay $49.50 more than what the market price is, but he does not have to, because when he goes into the store, there's a price tag on the item and it's $150. So he feels, or he at least considers that he saved $49.50 because he didn't have to pay what he'd be willing to pay. So if you go ahead and you add that up for each of the people along the way up to the market demand, then that overall is the benefit to the consumers because they're paying the market price and not what they would be willing to pay, if you have to interpret that in your econ class. So we take a look at the producer surplus. That's the lower of the two, and this is the overall benefit to the producers. So our integral is going to go from 0 to 10. Again, it's always 0 to the market equilibrium. And then we have the upper curve is the market price of 150 minus the supply function, which in this case is 10x plus 50. So if we clean that one up a little bit, ultimately our producer surplus integral is 0 to 10 of 100 minus 10x dx. Now we could go ahead and calculate the producer surplus here by fundamental theorem like we did with the consumer, and we had to use the fundamental theorem in the antiderivative for the consumer. But notice here that in our region, the producer surplus is a right triangle. We can actually evaluate this definite integral geometrically for that case. So we can use 1/2 base times height, which is a nice shortcut to kind of finish up the problem here. So the producer surplus is 1/2. The base is from 0 to 10, so 1/2 times 10. And then the height is going from the y-intercept of 50 on the demand function up to p sub 0, which is 150. So we have a height of 100. And so our producer surplus then, and you can confirm this if you'd like to run the fundamental theorem on this, is $500. And so that's the overall benefit to the producers in this marketplace. Again, if we just look at if only one unit was out there that was needed in the market, there would be somebody out there, according to our supply function, that would be willing to produce it for $60. But when they go and they put their item into the market, they see that they're getting $150 because that's what the market demand is at the moment. And so they are feeling this benefit to them of $90 more than they would have been willing to take for producing the item. So again, if you get into your econ class, you need to discuss what do these mean. That's what they mean. But in a calculus sense, when you talk about consumer producer surplus, it's an area between curves definition, upper curve minus the lower over the bounds. And it's just a matter of drawing it, defining your third function, p equals p sub 0, and that splits the area between supply and demand into two distinct regions. And then you can go ahead and define your integrals and calculate the consumer and producer surplus from there. If you'd like to learn more about business applications like consumer producer surplus or calculus in general, you can find them in my textbooks available for a nice price on Amazon. Don't forget to subscribe to the channel. Till next time, I'm P. Clark.